5.5, the definite integral. In this section, we're going to start talking about finding the area under curves on a closed interval. That's what a definite integral is. This first slide connects the idea of the integral to the area problem that we've seen in the last section. We'll talk about that in class. This notation should look kind of familiar. It tells us that the area under the curve is given by this. All of this looks familiar except for maybe the A and the B. We don't know what to do with those numbers yet. Our first example tells us to sketch the region whose area is represented by the definite integral and to evaluate the integral using appropriate formulas from geometry. So this 1 to 4, graphing the line y equals 2. We should all know how to graph the line y equals 2. Straight line that goes on forever. And we're looking at the interval from 1 to 4. We want that area. We should know how to find that area from geometry, maybe even earlier. It's a rectangle, the area is base times height, which would be 3 times 2, or 6. The calculus method of finding that same area would be to find the antiderivative of 2, which we know is 2x, and evaluate that at 2 points, 4 and 1. 2 times 4 is 8. 2 times 1 is 2. Subtract those two numbers. We also get 6. So we just saw a geometric and a calculus way of evaluating this area. Let's look at part B. Looking at a graph from -1 to +2. Of x plus 2. So we should know what that graph looks like. Looks like it starts at -1, 1 and works its way up to +2, 4. If we look at this shape and try to come up with a shape that matches it from geometry, looks like we have a trapezoid. And the area of a trapezoid is base 1 plus base 2 times height divided by 2. Best to think of this as a trapezoid that's lying down on its side because the bases are the two parallel sides. In other words, here's base 1, here's base 2. One of those bases we should be able to just count. We see that one of them is 1 and the other one is 4. Our height would be how far it is between the bases. In this case, 3. We get 7.5. That's the geometry method of calculating area. We can also do this same problem using some calculus methods. We'll see more about this in the next lesson. Calculus way of doing the same thing would be to find the antiderivative, x squared plus 2x. First we'll plug in 2. My antiderivative is wrong, it should be x squared over 2. First we plug in 2 and we get 4 over 2, which is 2 plus 2 times 2. So it looks like we get 2 plus 4 minus, then we plug in -1. Looks like we get 1/2 plus 2. So we get 6 minus, abort, this should not have been a plus, this should have been a minus. Yeah. So 6 minus -3/2, which also comes out to be 7.5. So we have a geometric and a calculus way to find both of these areas. Today's lesson's main focus is the geometric approach. That's what's most important for today. Part C. This one might be a little harder for you to graph. If you don't know what this graph looks like, you could do a couple of things. You could make a table. You could try to sit there and think about what can I do to make this look more familiar. It turns out if you square both sides, you get this guy, or we could rewrite that as so. Hopefully you recognize that version as a circle with radius 1. So there's our circle with radius 1, except we only want the values from 0 to 1, so I get rid of half of the circle. And because it's the positive square root, there's no negative in front, I only want the top half. So this graph is actually a quarter circle with radius 1. Using some geometry ideas, we know the area of a circle is pi r squared. This particular circle, we're only using a fourth of it, so we'll divide by 4. Radius is 1. We get pi over 4. We actually do not have the skills or abilities yet to do this same problem using calculus ideas. So this is an example of where calculus won't do the job for us and we'll have to fall back onto some old skills. You could type this into your calculator and it should give you pi over 4, but it will of course give you a decimal approximation in most of your calculators. In mine I get 0.7853. That's it. So next up, we're evaluating two more areas from 0 to 2 of x minus 1. So for x minus 1, first number I care about is 0. It's like I get negative 1. And when I plug in 2, I get positive 1. Something different's happening here. Looks like I'm crossing over the x-axis. And I can figure out where that happens by saying when does y equal 0? At 1. What this integral is actually giving us is not just area, it's actually called the net signed area. That hasn't been important up until this example because everything's been above the x-axis. Anytime we have an area underneath the x-axis, we consider the net signed area to be negative, whereas up above it looks positive. Using geometry, we've got a couple of triangles. We should be able to see pretty quickly that our area here is negative 1/2, our net signed area, and here positive 1/2. So our total area for part A, negative 1/2 plus 1/2, 0. Part B is only looking from negative, or from 0 to 1, so we only want that first triangle, negative 1/2. That's it. Net signed area is a little bit different from area. Now we got a couple of formulas that you do have to memorize, but they're not a big deal. First one, if your limits are the same, so it's like you're going from 5 to 5 or 7 to 7, you don't have a width, so your area is 0. The other formula we kind of have to memorize is if I switch the order of A and B, area, the net signed area stays the same, except its sign changes. So for instance, if I know 2 to 7 of f of x equals 12, then my conclusion is from 7 to 2 of the same function would be negative 12. Flipping those limits changes the sign of your answer. We'll see that, I believe, in the next example. So example 3, the whole thing becomes 0 no matter what's on the inside of the function because those limits are the same. Part B, we figured this out earlier. I lie. We figured out the other version of that earlier, where the 0 was here, the 1 was up here, and that came out to be pi over 4. And because those limits are flipped, our new answer becomes negative pi over 4. This theorem says we're allowed to split up the integrals in ways that we want to. Addition and subtraction can be split up. Constants can be pulled out in front of the integral sign. All that really means is we can take a complicated looking function and break it up into smaller, more manageable pieces, which we will see right here. So looks like we've got, looking at 0 to 1, I'm going to break this up. I'm going to take that 3 to the outside because I'm allowed to, it's a constant. Now some beautiful things happen. We saw in a previous example that this whole thing becomes pi over 4. So I can just rewrite it as pi over 4. The first one looks like it is a rectangle that's 1 unit wide and 5 high. So we should know the area of that is 5. So we get an answer, 5 minus 3 pi over 4. Done. At this point, go ahead and pause the video and try all of these guided practice. Good luck.